is about reactions. Chapter 17 is about reactions of aromatic compounds, and we are going to look at some electrophilic substitution reaction first. At the end of the chapter, we talk about nucleophilic substitution reaction for aromatic ring. In chapter 16, we looked at the structure for aromatic compounds, and aromatic means stability. So a molecule that is aromatic, let's say if you have benzene ring, that's everyone knows about benzene ring, it's aromatic ring. If you add like a Br2 or Br as a Br2, there would be no addition reaction. So addition reaction does not take place, because if addition takes place, let's say if addition takes place in somehow here, and a Br is added, what's going to happen? You go from aromatic to non-aromatic. And going from aromatic to non-aromatic is going from more stable to less stable, more stable reactant to less stable product. And for those reasons, this reaction does not take place. But instead, if you add proper catalyst, you can actually have substitution reaction. When you are dealing with the benzene ring, just pay attention to this, that each carbon carries one hydrogen for benzene ring. So you have a hydrogen on each carbon. The general formula for benzene ring is a C6H6. If you draw the loose structure, you come up with 3 pi bond, and each carbon would take one hydrogen. If you use proper catalyst and add the Br2, the catalyst that is used is called FeBr3, and you add Br2 using proper catalyst, you can do substitution reaction. So what happens in this reaction, the aromatic system will be maintained. You have aromatic ring there, and one of the hydrogen would be replaced by bromine. The type of reaction here is a substitution reaction, because bromine is going to substitute the hydrogen, or hydrogen is being substituted by bromine. So the type of reaction is called substitution reaction. So there are 3 steps in this reaction. In step 1, you have to have like a very strong electrophile. Your electrophile must be very aggressive, because aromatic system is stable. Plus to attack the benzene ring. So you must have a very strong and aggressive, electrophile. So when you have the electrophile, then a strong electrophilic attack, or the benzene ring basically will attack the electrophile. So that's what is demonstrated here in this part of the diagram up here. The benzene ring, because it's rich in electron, is going to attack the electrophile. The attack, or the arrow, is always from electron rich to electron poor. So if the E plus is our electron poor species, or our electrophile, the attack is going to come from the benzene ring toward the electrophile. And the next step, which is this your second step, so first step, strong electrophile is being attacked by the benzene ring, or electrophilic attack. Second, the resonance is going to form for our intermediate. We have like a sigma complex. The sigma complex is going to go through few resonances, and when the more number of resonances or greater number of resonances, the more stable the intermediate is going to be. And the next step, the hydrogen is removed by a base. So you get the hydrogen being removed by a base. When hydrogen is removed, the electrons that they were used for the bond from carbon to this hydrogen is going to be dropped in, and the aromatic system is going to be maintained again with the loss of protons. So hydrogen is leaving and the electron is going back to maintain the aromatic stability. So pay attention to these three steps. The emphasis is going to be on these three steps. The difference is going to be what the new electrophile or different electrophile that you are going to bring in. And then if you have a simple benzene ring or you have a substituted benzene ring, for example, if you have a CH3 here, instead of benzene, if you have a toluene and you bring a Br2 with the toluene, would the Br go to position 2, position 3, or position 4? That's basically the summary of this whole chapter, but we have a lot of different reagents that you have to memorize those reagents. So the emphasis is on these steps that is going to take place. Electrophilic. So we have this diagram. You have again attack on the electrophile from the sigma complex, or to form the sigma complex. Okay, forms the sigma complex. So from the benzene ring, the attack on the electrophile. Sigma complex is formed. What is called sigma complex? Each one of these are sigma complex. It's the time that the electrophile is being added to the benzene ring and before hydrogen leaves. So hydrogen is still intact. So one of the carbons actually has both electrophile and the hydrogen. And when this hydrogen is removed, then you end up with the product. So before the hydrogen is removed and while the electrophile is attached at the same time the hydrogen is attached, the complex is called sigma complex. The sigma complex would go through multiple resonances, and that makes the intermediate, which is the sigma complex, more stable. A base, that could be the solvent, or it could be the base or the catalyst that you actually used it partially. And the first step now is coming back and removing hydrogen. And when it does remove the hydrogen, the pair of electrons is going to drop into the ring and the pi bond forms or regenerates, and we have aromatic ring. So aromaticity is back now. Okay. So I have a couple steps that I have to take going from one slide to the next. And this slide example, the top example that we have here is demonstrating the addition reaction. So if addition reaction takes place, the aromatic property is going to be destroyed. So it goes from aromatic to non-aromatic, as I had on the earlier slide for you. And that's why it's going to be impossible. There's no reason or no desire for this reaction to happen, because the reactant is a lot more stable than the product. But if you are using this combination of the Br2 with proper catalyst, so you have to use this proper catalyst, substitution reaction would take place, and Br would be substituted by hydrogen, or hydrogen is Br is replaced by the Br. This reaction is an exothermic reaction. So exothermic reaction usually is more favored or more spontaneous, or it can happen based on the thermodynamic values. It could happen. Now, the general reactions for like bromination, chlorination, iodination, sulfonation that you are going to learn, nitration, all these reactions, they follow the same three steps that we had on the first slide. The difference is how your electrophile or a strong electrophile is being generated from one reaction to another reaction. So you need to know those steps, or steps to generate a strong electrophile or a stronger electrophile. for the first step or for the electrophilic attack. So if you have Br2 is close to noble gases, is on the right side of the periodic table, and it has high electronegativity, but is not a very strong electrophile. But if you bring the FeBr3 to react with Br, how would you classify FeBr3? FeBr3, if you draw the loose structure for FeBr3 with using all of the valence electrons, then is going to have empty orbital. It's not satisfied by the octet rule. Fe has only 6 electrons because halogens, they cannot form double bond. So even though you have pair of electrons here, 3 pairs of electrons on each bromine, but they are not allowed to form double bond. Halogens do not form double bond. Iron is electron deficient here. And if it's electron deficient, is acting as a strong Lewis acid that accepts pair of electrons. So it's electron deficient, is going to attack this bromine, remove bromine with pair of electrons. And if you remove electrons, bromine with pair of electrons, the other bromine is going to gain the plus charge. So the other bromine with the plus charge is a strong electrophile. So Br with the plus charge is going to be very strong electrophile, or stronger electrophile than the Br2. So the Lewis acid that we are using as a catalyst is FeBr3, is going to remove one Br with the pair of electron, and it would change to FeBr4 minus actually. Okay. Now, if you bring the Br, the fourth Br here with the pair of electrons, now is going to be satisfied with the octet rule, or octet satisfied, but the other Br would carry the plus charge. The Br carrying plus charge is a disaster for that Br, because Br is highly electronegative, and because it's highly electronegative, doesn't want to have a plus charge. If it doesn't want to have that plus charge, is going to be considered as a very strong electrophile. So then electrophilic attack would take place. The Br with the plus charge would go into the benzene ring, is going to use the pi bond to form the new bond, because you have that this bond that is forming between the Br and the benzene ring is actually using the same electrons that you have in the pi bond, because the Br with the plus charge doesn't have any electrons. You see that Br, the minus, this was like a heterolytic cleavage, because you remove one Br with 1 electrons as a Br minus that it shows up here with the Fe. The other one leaves with electron deficient and is going to be the Br plus. So Br plus brings the plus charge to the benzene ring. So if the Br comes in, the other carbon, you see this carbon-carbon double bond, when the double bond is moving up here to form the Br bond, the other carbon is going to take the plus charge. So we have the plus charge on the other carbon, okay? Now, this is the sigma complex. This is called sigma complex. Electrophile comes in, the hydrogen still is there, it has not left yet. It's called sigma complex. The sigma complex can go through resonances. Basically, to go through resonances, the pi bond is going to move around and the plus charge is going to move for the new resonances, and I can show you how they are moving. And at the end, when the base, like in this case, FeBr4 minus is acting as a base, when it removes the hydrogen from the sigma complex, the pair of electron drops in and the pi bond is regenerated. The net result is a substitution of hydrogen with the bromine, and the reaction is called bromination. What you need to know is that your reactant is benzene. The reagents are Br2 and FeBr3. The product is bromobenzene. So any of two of these can be given, and the last one can be asked. So if this part is not given, then you should be able to write what are the reagents, or if the reactant and reagent is given, you should be able to write the product. So make sure you memorize the reagents. You do need the reagents for this chapter. To survive this chapter, you have to memorize lots of reagents. And that's all it is, to memorize all these reagents. So if you have like a couple of weeks time before your exam, you start memorizing all these reagents for chapter 17 now, you have a great chance to do much better and do great on the exam than if you don't memorize these reagents for chapter 17. Okay, this diagram, it shows the formation of the sigma complex. That is a time that electrophile has been attached to the benzene ring. Before hydrogen leaves, you have your intermediate called sigma complex, your reactants, and the product. The reaction is a two-step reaction, and the slow step of the reaction is the rate determining step. Fastest step of the reaction, is not involved in the rate determining step of this reaction. Okay, how is chlorination or iodination different from bromination? For chlorination, is the exact same thing. So for chlorination, you would start with the okay, I hope it doesn't. With the chlorination, you start with the benzene ring. You add Cl2, AlCl3, or FeCl3, either one. And then the product is going to be Cl. The mechanism is very similar to bromination, because if you look at the Lewis structure for aluminum chloride, it's similar. So your Lewis structure would show that you have electron deficient Lewis acid, aluminum chloride. This can remove electrons from chlorine, because chlorine can be attacked by this. Aluminum chloride is going to remove chlorine with the pair of electron. This side is going to be Cl plus. Cl plus, Cl just like Br, because it's highly electronegative. If you put a plus charge on it, it makes it very unstable or very reactive, because like oxygen, like nitrogen, and any halogens, they do not like to have that plus charge. So it's going to make it very unstable and very reactive. Aggressive enough or strong, very strong electrophile to attack the benzene ring. So for chlorination, very similar to the bromination, you could use either aluminum chloride or FeCl3, either one can be used as a catalyst. So, or FeCl3, that's for chlorination. For iodination, they use the iodine and the strong acid, or a strong oxidizing acid, and strong oxidizing acid can generate the I+. And what we care is the strong electrophile. That could be the Cl+, Br+, or I+, and the reagents that is going to yield to formation of that strong electrophile. But after you have the strong electrophile, you see the pattern or the steps after that is all the same, because benzene ring is going to attack the I+, sigma complex is forming, with the sigma complex, you see the just movement of the electrons. The pi electron is going to move up between the carbon and the iodine, and you have this new bond here. Because the carbon right here, this carbon is losing pair of electron, it's going to gain the plus charge. Now you have your sigma complex. This is going to go through resonance. How does the resonance forms? The way that the resonance forms, a pi bond is going to move by one bond. You can change the color here. A pi bond is going to move by one bond. So the pi bond will shift to the next carbon, and plus charge is going to jump by two carbon. So you see the plus charge is coming up here, is jumping from carbon sigma to the two carbon later. So it goes from one, you have it right here. So it's 1 and 2. Okay. So plus charge moves by 2 carbon, and the pi bond moves by 1 bond. Then you see this plus charge that we have here is allylic with the pi bond up here. So it can form another resonance. The pi bond is going to move by 1 bond, and plus charge is going to move by 2 carbon. And then you end up with the plus charge up on that carbon. And there is no, other resonances. It kind of stops here because you don't have a pi bond on the, like clockwise, you don't have a pi bond to move up. And on the counterclockwise or on the left side, if you have a pi bond, if you move the pi bond, you kind of go back to the previous resonance that you have. So there is no benefit, it's not going to happen. So that limits the number of resonances to only 3 resonances for this sigma complex. So we have 3 resonances here. So the resonances is going to stabilize the sigma complex. What's the next step? On the next step, the solvent, like water, because water has pair of unshared electrons, or 2 pairs of unshared electrons, and water can act as base, can remove hydrogen from the ring. When it removes the hydrogen, is going to remove it as a H+. That means the pair of electron is not needed or doesn't move with the hydrogen. So pair of electron drops in and forms a new, it forms that new pi bond, and it regenerates the aromatic system. The net result is replacement of hydrogen by iodine, and the reaction is called iodination. Okay. Iodination. Any questions? So we learned about 3 reactions already: bromination, chlorination, iodination. You need to know the reactant, the reagent, and the product. Besides, you need to know the mechanism on how the electrophile or strong electrophile is formed. For chlorination, aluminum chloride is going to remove chlorine with pair of electrons, with pair of shared electrons, to form the Cl4, and then the Cl that is removing the electrons, the other Cl would be electron deficient. It counts as the strong electrophile. When you have strong oxidizing acid with the iodine, it would generate the I+. It would oxidize the iodine and changes to I+, and that's our strong electrophile. For bromination, FeBr3 removed the Br from Br2 with the pair of electron. The other Br was plus charge or a strong electrophile. Questions? Any questions? And once in a while, I have to make sure that you can hear me. So good. Okay. The reaction, if it's like in terms of the number of steps of the reaction, because is a 2-step reaction, then it makes it like a SN1 type reaction because it's a two-step. So carbocation that forms here has a specific name as a sigma complex. So it is like a carbocation because you do have that plus charge cycling in the benzene ring, and it's jumping like every other carbon, and it gives you like 3 different resonances. So it makes the carbocation or the intermediate more stable because there are like 3 resonances. When you have a carbocation formed, and carbocation can go to resonances like for allylic, benzylic, or sigma complex, it's going to be more stable. But the key is to start this reaction. To start this reaction, you don't have a leaving group to leave. So what's going to happen, the electrophile is going to come in first and just removes the pi bond. So it is like SN1 and it's not like SN1. In one aspect, that is a 2-step reaction, it's like SN1, but the fact that you have to bring in the electrophile in first before the leaving group, which is the hydrogen, is being removed, that's different. That part is different from the SN1 type reaction, because that was a question on the chat, like how similar is this to SN1? It is only similar based on the number of steps. Yes. Okay. Bromination of this compound. What should be the product when you do bromination for this? Okay. For the bromination, it can go to it's going to form bromine forms bond on the ortho position with respect to this nitrogen, and the rest of the second part of the chapter emphasizes on like the directions or directors, what we have already on the benzene ring. The new coming is going to go to which part. So the nitrogen that we have here with the pair of electrons is going to activate this benzene ring, and is going to activate it a lot. And since it's going to activate it a lot, then because it's very reactive, that's the reason you don't see the FeBr3 here. No need for it. If you add it, it's going to make the reaction even faster. But because of the activating group that we have on the benzene ring, because of the nitrogen with the pair of electrons, or any electron donor group is going to activate the benzene ring. Because it's very highly activated, this reaction can take place without the presence of catalyst. But if it was a benzene ring, right here, you would say no reaction. Okay. If it was a benzene ring, you would say no reaction here. You didn't have any product. Okay, next, we have new experiment. You have done experiment in the lab, experiment 14, nitration. And for the nitration, again, this is the nitration of the reaction, shows the nitration of the benzene ring. The general steps for the reaction is the same 3 steps that we have. We have to have a strong electrophile first to be to attach to the benzene ring or attacks the benzene ring. Then the sigma complex forms, then hydrogen is removed, and then you have the product. Okay, so the question is, what is the strong electrophile in the nitration process, and how is it formed? This step here, it shows the mechanism for how our strong electrophile is forming, and that is like NO2 plus. NO2 plus, nitrogen is highly electronegative, oxygen is highly electronegative, and if NO2 carries a plus charge, again, it makes this very strong electrophile, because neither one of them likes to have that plus charge in. So we will have, if we can generate NO2 plus, which is called the nitranium ion, we have the first step. So that's major concern for every reaction for benzene ring or electrophilic substitution reactions. How do you make that strong electrophile? So this is our strong electrophile for nitration. Okay, strong electrophile. In order to make that, you have to mix sulfuric acid with the nitric acid. When you mix sulfuric acid with nitric acid, what happens? Nitric acid is going to be protonated, so this OH is going to change to OH2, and then with the plus charge, okay, with the plus charge, then H2O would leave. You end up with NO2 plus. So when the nitric acid is being protonated, one of the OH from the nitric acid would gain a hydrogen. You don't, when you remove the H2O, the plus charge goes back to the nitrogen. So you have the NO2 plus. The NO2 plus is a strong electrophile. So benzene ring is going to react with that. The pi bond is consumed to form this new bond between the electrophile and the benzene ring. And that used to be between carbon A and carbon B here. So that red bond used to be between carbon A and carbon B. Now that you remove it to form bond with the carbon A and nitrogen, carbon B would take that plus charge. So since carbon B has the plus charge and hydrogen still there, it's called a sigma complex. The next step would be to remove the hydrogen from location that you have the electrophile or NO2, and you end up with the product. The net result is removing H and substituting with NO2, and that reaction is called nitration reaction. The reagents for nitration is HNO3 and H2SO4. So remember this as the reagent, and it has to be mixed together. You're not adding one after the other. If you were adding one after the other, it would have been like 1 and then 2. Okay, if they're not separated by number, that means they're added together at the same time. And if you remember from your experiment, you actually mix the nitric acid with sulfuric acid in a separate test tube, and then you mix with your acid analyzers. After you do nitration, basically you replace the hydrogen with the NO2. You can reduce this. What is reduction? In organic chemistry, reduction meaning adding hydrogen. So adding H2 or 2 hydrogens, that's called reduction. Removing oxygen is reduction. Both of them is called reduction. Okay. Reduction. So if you have a strong reducing agent, you can remove oxygens and you add hydrogen. So this is like a 3-step reduction. You're removing 2 oxygen and you're adding 2 hydrogens. So it's like a 3-step. So you have to use a strong reducing agent. The strong reducing agents that you're using here, it's like a zinc mixed with HCl. So it's zinc HCl. Okay, you don't have to add all of them at the same time. If you use zinc and HCl, that's a strong reducing agent. It will reduce NO2 to NH2, or you use the tin and HCl. So that's how it works. Okay, either one of them with the HCl, okay, or Fe with HCl. But the point is that in order to make the NH2, you don't have a reagent to go from benzene ring. Okay, you cannot go from benzene ring to NH2 directly. You cannot do this. Okay, what you have to do, you have to first take this to NO2, and then go to this. You can't go directly. Okay, this doesn't work. There is no direct method to go from benzene ring to aniline, but you can go to nitrobenzene and then reduce it to aniline. Okay, sulfonation. So you learned about bromination, chlorination, iodination, nitration, reduction of nitration, and now is sulfonation. There are like multiple reagents and the reaction, different type of reactions that you have to be worried about memorizing the reagents for. They are not very hard, but you just have to do practice. And if the assignments that you have for the chapter is not enough, like do the end of the chapter problem, every other problems. The more you practice with the end of the chapter problem, the better you remember these reagents, because you are using it like often and under different conditions you would use them. So next reaction is sulfonation. What is happening in sulfonation? You are removing, so there is a hydrogen in every carbon here. So you remove a hydrogen and you add SO3H, and the SO3H is called the sulfonation substitution. Okay, so this reaction is a reversible reaction. What does it mean is a reversible reaction? Because sulfonic acid can be added to benzene ring, it can be removed. If you use fuming sulfuric acid, with the fuming sulfuric acid, which you have, like you don't use any water, it's just you add the sulfur trioxide to like a 7% of the sulfur trioxide to sulfuric acid, is going to even make it like more concentrated sulfuric acid. Then it's called fuming sulfuric acid. That would be the reagent. If you use like dilute sulfuric acid with some water, is going to give you these, remove this and replace with the H. Okay, so when you see this double arrow, that means that this product is not very stable. You can make sulfonation, you can remove sulfonation, or you can remove the sulfonic acid branch from the benzene ring as a reversible reaction. So your reagents, you would call it like a fuming sulfuric acid. You can use the word fuming sulfuric acid, or you could use SO3/H2SO4 as the reagent for sulfonation. The sulfur trioxide, it acts as the electrophile, strong electrophile in this case. When it forms bond with the benzene ring, it's going to generate that the plus, and then the minus charge is just the resonance that is forming here, because the pi bond is used to form the bond between the carbon and sulfur, and the pair of electron from the pi bond between the sulfur and the oxygen is moving up and gives a negative charge. So if you protonate this, you protonate the oxygen with the negative charge, you get the sulfonic acid as the product. So this hydrogen needs to be removed, and that hydrogen is going to be removed with the conjugate base of the sulfuric acid. The reaction, all steps are reversible. So since all steps are reversible, sulfonation, if you have sulfonation, we also have like desulfonation. So what does desulfonation means is that if you add like dilute acid and heat, you can remove the sulfonic acid and change it back to benzene ring. What's the purpose of this, and what's the application for this? Sometimes You want to protect like one group. You don't want something else or another, let's say bromine or chlorine, to get to this position. You can do sulfonation. You can protect that group, and then when you are done with the reaction, you just add dilute acid and drop this group. So it can be used as like protecting group. You would learn also about the protecting group. Sulfonation, it can be used as one of the protecting group. So because of the desulfonation being so easy, you can add the sulfonic acid. You can remove the sulfonic acid by adding dilute sulfuric acid to it. So sulfonation, nitration, chlorination, bromination, iodination. And then reduction of the nitrobenzene. Those are the reactants so far, and you need to know the reagents, all of the reagents. Okay. Now, so far, all the reactants that we were dealing with was like a benzene ring. And what happens if there is a group already on the benzene ring? Now, if we have the CH3 here, which so instead of benzene, you start with the toluene and do nitration. What would be the product? So if as soon as we see this combination of HNO3, H2, SO4, we have to recognize this is a reagent for, what's this reagent for? A reagent for nitration. That means it's going to generate NO2 plus, and NO2 plus is going to replace one of these hydrogens. Okay. Just remember, if you have a CH3 here, there is no hydrogen because you have the benzene ring already with the aromatic, pi bonds, all 3 pi bonds are there. So if you have CH3 or any branches on benzene ring, that means there is no hydrogen. Now, this NO2 that is produced from nitration reagent, how do I know it's a nitration reagent? Because I know that HNO3 and H2SO4 mixed together is going to give me nitronium ion, and that is a nitration reagent. So this is going to replace one of these hydrogens. If it does replace the hydrogen A, you would get this product, okay? If it replaces hydrogen B, you would get this product. If it replaces hydrogen C, you would get this product. So you get these 3 products. If it replaces hydrogen D, what would you get? Hydrogen D, you would get, you count from this side, carbon 1, 2, 3. So D is going to also come here, okay? If it replaces hydrogen E is going to be 1, 2. So it's going to be this. So we have 2 positions, 2. They're identical. And then we have 2 position 3. These 2 are identical. 2 position 3. 2 position 2. Those are the purple ones. And then 1 position C that we have here, or 4. So the possibility of formation for 3 different products. If we have more than 1 product, then we have to have a logic and explanation which one is the major product. And if there is a major and minor product, if it's not distributed like evenly, like if we have 3 possible products, it's not 33% for each, then we have to have explanation why one is more, preferred over other. So by looking at the numbers that are given in this reaction, because it gives us the numbers, 60% of ortho and 36% of the para, 60% of the position 2, 36% of position 4, and only 4% of position 3 is being occupied. So position 2 is known as ortho, and position 4 is known as para. Okay, this is a 1, 2. position, and para is a 1,4 position. But position 3, which is a 1,3 or meta position, it has very low percentage. So even though we have two possibility for meta, two possible position for meta, but the total percentage we are getting from that is like a 4%. And that's very low and is negligible. So the major product is either ortho or para. So we have either ortho or para. And then based on the locations, these are ortho meta positions, and this is a para position. We have 2 ortho position, 2 meta, and 1 para position. And based on this percentage. So now there should be some explanation. The observation for this reaction shows that this reaction actually takes 25 times faster than benzene. That means if you add CH3 group to benzene ring, it's going to make the benzene ring more reactive. So this group is known as activating group, or is an activator. So methyl group is an activator because it made the benzene ring more reactive, because this reaction is much faster than benzene itself. When you get a mixture of the product and you have an activating group, the new coming group, it will go to either ortho or para position, and that becomes the rule from now on. So if we have activating group, it will activate the ortho position and it will activate the para position. So for electrophilic substitution, the new coming branch, it will go to either ortho position or para position. Now, if you look at this, if this is 36, we would expect this to be 72, right? Double of the para, but is less than the double. If this is 36, or if this is a 60%, this is expected to be 30% because you only have 1 para for every two ortho. What makes the para to have this ratio compared to the ortho is basically showing that we expect to have less para, but we have a little bit more para than what is expected. Any idea? What can cause ortho to be less than what is expected? There is a group right here, and is the group of ortho or position of ortho is hindered by methyl group, but para position is wide open. There is no hindrance, steric hindrance there. So steric hindrance, it blocks the ortho position slightly, but since this group of methyl is not too large, then we only see a decrease by that much. It just shows like 60 to 36. If this group is like huge, if you have like a T-butyl group in there, this is going to be even lower because you have more steric hindrance. So ortho position are sterically hindered by the group that is there already, but para position is not going through steric hindrance. There's no problem with the para position. So if we have an activating group, for activating group, the product is going to be on the ortho. When we have the electrophilic substitution reaction, the product is going to be more ortho and para. So if we have the benzene ring, this energy diagram, hopefully with the energy diagram is easy to explain, and then we look at the resonances. If you have benzene ring versus toluene, which one is going to be faster? Benzene or toluene? Basically the blue color or black color? the line. Toluene is going to be faster because it has less energy, is more stable. The sigma complex that is coming from toluene is more stable than the sigma complex coming from benzene ring. So the explanation there is presence of CH3 because CH3 is the activating group. The group is activator, and it's going to be faster. But in the meta position, if you look at the ortho and para position, it's even more stable. And the reason is more stable is explained in this diagram here. That if it goes to ortho or para, you would have advantage because you have one of the resonances, at least one of these resonances is going to be tertiary carbocation. In this case, you have a tertiary carbocation when the NO2 goes to the para position. So you have 3 resonances. One of the resonances is tertiary carbocation. If you had a meta position being attacked, and I will show you on the next slide, all of these sigma complexes is going to be secondary. There is no tertiary. See, the difference is like very slim. It's just one of the 3 resonances that it's tertiary for ortho. It's tertiary for para. But if you look at the meta, for meta, they are all secondary. There is no tertiary. And that makes a difference in where the substitution is going to go, because the more stable intermediate would yield to major product. So if we are looking at this possible product, ortho and para is going to be major product, meta is going to be minor product. Even though meta is better than or faster than the benzene itself, but we are not comparing the benzene with the ortho and ortho para and meta. We are just comparing the meta position with ortho para position. So for both ortho and para, one of the resonances is a tertiary resonance, and that's going to make a huge difference or a major difference in the percent composition of the product. For meta, we don't have that. So if we do bromination now, instead of the methyl group, we have ethyl group here. For the ethyl group, because it's larger, it's bulkier than the methyl group, you see our ortho is not 60% anymore, it is 38%. And for para, now we have 62%. Because of the ethyl group is being bulky, the bromine prefers to go to the para position rather than the ortho position. But meta position is even lower than before. It's just less than 1%. So ethyl group is more electron donor than methyl group because it's bulkier, it's larger group. At the same time, is activating group. At the same time, it's sterically hindering the ortho position. So the percentage for this. So if you get like a question, like if you have toluene versus this, for the toluene, we just saw that ortho we had for toluene, if this is a CH3, if this would give us like a 58%, but for ethyl group, we get 38%. How would you justify it? Basically, is the steric hindrance that is coming from ethyl group. Okay. OCH3, the question is OCH3 or methoxide, is it ortho-para director or is it meta director? If we draw the resonances for the ortho position, we have, first of all, before, for the toluene, we had only 3 resonances. Here we have 4 resonances. Okay. And if this is like we have 4 resonances and you have one that is especially more stable, then 4 resonances versus 3 resonances is going to make a huge difference in the stability. So with the pi bond, that the reason this pi bond can form here is because pair of electrons from the oxygen can drop in to form this pi bond. Like for CH3, we didn't have that pair of electron. So there is no like a, resonance by the pi bond for toluene. But for alkoxide or for methoxide specifically, we have this pair of electron that can drop in and form a resonance number 4. So we have 4 resonances and it's going to be more stable. And that's why ortho and para attack for this compound with the activating group of alkoxide is going to be more stable. So the product is going to be orthopara, not meta. And the explanation goes back to how many resonances you have when there is an ortho and para attacked, compared to if you had, okay, compared to if you had only meta. Okay, if you have a meta, if this is on the meta position, you only get 3 resonances, not 4 resonances. So for 3 resonances is less stable. That's why the percentage composition of the product for ortho and para is a lot more than the meta position. If you do bromination for the anisole, anisole is like benzene ring with this methoxide group attached to it, because it's highly activating group. So anisole or methoxide is highly activating group. It's very reactive, and you don't need to have the ferric bromide as a catalyst. You can just add bromine, and this can go like a tri-bromo product. And both ortho position and a para position can be brominated. So this is a methoxy group because it's so strongly activating that it can go tri-bromo or tri-brominated product without a catalyst. So it's just showing that it's being activated. NH2, activating or deactivating group. NH2, because of the pair of electrons that you have on the nitrogen, is going to be activating group. And if it is activating group, the product is going to be ortho para, not meta. Now, if you have a deactivating group, the product is going to be meta because ortho and para position will be deactivated. So these groups that you have here, there's some pattern that you can kind of memorize it, or just look at the alkyl group. We know that they are electron donor. So we know anything that is electron donor or electron rich is going to activate the benzene ring. If the element directly attached to benzene ring has pair of unshared electron, like if you have alkoxide, oxygen attached to the benzene ring has pair of unshared, 3 pairs of unshared electrons, is going to be activating. So nitrogen with pair of electron, hydroxide when with the pair of electron, or alkoxide, these are activating group. If you compare, let me do this, and I want you to help me with this. Compare A and B. Which one is stronger? Obviously, if you pay attention to this sign, A is a stronger activating group than B. But can you see the reason why B is less activating compared to A? Can you see that? Can you tell me? What makes B less activating than A? What makes benzene ring activated, or what activates the benzene ring is the pair of electrons that you have on the element directly attached to the benzene ring. If you have this CO double bond group, CO double bond is carbon is losing electron to the oxygen. So carbon is a slightly positive. And since carbon is positive, it's going to remove some electron from nitrogen. So it's not helping nitrogen with the pair of electron. So the ability of nitrogen to share electron or donate electron to the benzene ring is going to be reduced. That's why A is a better activating compared to B. So this reaction, if you have A, it's going to be much faster than B. Okay, so that is the pattern, and these are the just examples. Okay, so if you have like a aniline, or if you have phenol and then phenyl ether, the order of which one is stronger activating or weaker activating group. In general, when you have when you have a donor group, so G stands for giving or electron donor group or activating group, they are ortho and para activators. If you have electron withdrawing group, okay, if you have electron withdrawing group, the ortho and para is going to be deactivated, but meta position is left out. So meta position is not deactivated, only ortho para is deactivated. So if you have electron donors, is going to be activated also. But when you have these groups that they can, give electrons, transfer electrons, they are going to be strongly activated. So what do you think of NO2? Activating or deactivating? If I put the NO2 like this, NO2 is pulling electron, oxygen is pulling electron, so nitrogen doesn't have electron. It's going to be positively charged. As a result, it's electron withdrawing group, so it's not activating group, right? Is going to be the opposite, is deactivating group. And if you are using deactivating group, this is a strong deactivating group, NO2 is a strong deactivating group. And if you are adding another NO2 group, how do I know that I'm adding NO2 group? Because as soon as I see this mixture of HNO3, H2SO4, I know that I have a nitronium ion that is going to replace the hydrogen. The question is which hydrogen is going to be replaced, ortho, meta, or para? If you look at the percent composition, meta position is the major product. And why meta position is major product? Because the group that is already on the benzene ring is a deactivating group, or it is electron withdrawing group. Questions? No questions. Okay. So if you have the NO2, as soon as the electrophile comes in, when it's if the electrophile goes to ortho position, you would get the carbocation forming in the sigma complex facing this the nitrogen with the plus charge already on it. And these two plus charges is going to next to each other because it's electrostatic repulsion, basically, like charges, they repel each other. It's going to make the molecule very unstable. So this makes it especially unstable. So when you have electron withdrawing group, ortho position is not favored. For electron withdrawing group, para position is not favored either, because in one of the resonances you are going to have problem. Okay, one of the resonances you are going to have problem with the plus charges being next to the deactivating group. Perfect. Deactivating groups, it's meta director, or electron withdrawing groups are meta director. So the next group would go to meta position, but activating group, the other name for them is electron donor groups. They are ortho and para directors. Very good conclusion. Yes. Okay, so this diagram up here, it's comparing benzene ring with the benzene ring carrying deactivating group. Is saying benzene ring is going to be better off not having an O2 on it anyway. Benzene ring is going to be more reactive than if you have electron withdrawing group. But when you do have electron withdrawing group on it, the meta position is better than orthopara. So electron withdrawing group can help the next group go to meta position, because when it goes to meta position, the intermediate is going to be more stable compared to orthopara. But if you don't have any electron withdrawing group, the benzene ring itself is going to be better off without any electron withdrawing group. So deactivators, and they are meta directors. So if you have electron withdrawing groups, they are deactivators, and they are meta director. So how do we know is the deactivating group or is the meta director? The element that is directly attached to the benzene ring basically has a plus charge. Let's say if I have carboxylic acid functional group here, COOH, you see oxygen is pulling electron from carbon. This oxygen is pulling electron from carbon. Basically, carbon is going to be plus charge. I'm not talking about the carbon on the benzene ring. I'm talking about the carbon attached directly to the benzene ring that carries the plus charge. So if it carries the plus charge, it cannot give electrons to the it's basically withdrawing electron from the benzene ring, and is known as deactivating group. Ketone functional group, CO double bond, a carbonyl group, same thing, is going to be deactivating group, because the oxygen is pulling electron and the carbon feels positive. So it's going to be a meta director. So some of the other deactivating groups, and if you look at any of the Lewis structure for any of these groups, you find that the carbon or the element directly attached to the benzene ring, it carries a plus charge. So two of the resonances, sulfur has plus charge. And then here nitrogen has plus charge. So if the element directly attached to the benzene ring has positive charge or partially positive charge, the group is known as deactivating group. Exceptions for halogens. Halogens, they are deactivating groups, but they are not meta directors. Halogens, they are ortho-para director. We just have to memorize that. Halogens, they are ortho-para director, even though they are deactivating. Okay, they are deactivating, but they are ortho para directors. Okay. So if you have halogen on the benzene ring, it's deactivating, because with the halogens you have more of a, more energy or for the intermediate, higher energy for the intermediate, so it's less stable than if you had the benzene ring itself, but they are ortho-para director. And this table basically is going to help you, easier to see all in one place and memorize it. Electron donors group, like alkyl group or phenyl group, and then pi donors. Those are the elements that they have pair of unshared electron on the element directly attached. There is no plus charge, but you have pair of unshared electron. It can donate electron, or they are called like a pi donors. Then you have like a sigma donors. These are electron donor groups. And then you have halogens, which is like exceptions. They are deactivating, but they are ortho-para directors. And then you have your carbonyl groups. All carbonyl groups, they are deactivating. And then you have anything that has element attached to higher electronegativity. So sulfur is attached to oxygen, carbon is attached to nitrogen, nitrogen is attached to oxygens, and they are deactivating group. This group here has a plus charge. If it has a plus charge, you don't have to look for a reason. It's going to be electron withdrawing group. Okay. I don't want to give you, I can stop here. I just want to just this last slide. What happens if you have more than one substitutions on the benzene ring? Who is going to tell where would the next group go? So if you have a CH3 group here and you have an NO2 group here, now you're bringing another NO2, right? How do we know we are bringing NO2? Because this reagent mixture is for nitration and is going to give us an NO2 plus. Would it follow the rule from CH3 or would it follow the rule from NO2? NO2 is a deactivating group, is a meta director, and CH3 is a ortho-para director because it's activating group. So I usually say this like look for the positive attitude, look for something that is like activating, or even if you have two activating, look for the stronger activating, and don't mix the effect of both of them. You first of all decide who is going to rule regardless of what is coming in. You have an electron donor group, electron withdrawing group. So electron donor is going to rule here. Then the next group is going to go where the electron donor is telling to go. This electron donor is saying go to ortho position or para position. The para position is blocked, so it's going to go to ortho position. Okay. Between these two groups, this is electron withdrawing group. This is electron donor group. Okay. So if you have a donor and withdraw, just ignore the withdrawing group. Go with the donor. The donor group says go to either ortho or para position. So it's going to go to either ortho or para position. So before looking at this reagent, what's going to happen next, compare these two. If you have a withdrawing and donor, just ignore the rule of the withdrawing. Just go with whatever the donor or activating group is going to direct. So it would go to the, because it's an electron donor, it would go to ortho para position.